In this video, we'll go over schema refinement and normalization. We'll specifically look at functional dependencies and what does it mean and what we can do with functional dependencies. So in the previous videos, we saw how we can use ER diagrams and to model a given data problem, and that's a good start to begin thinking about the logical schema design. Then from there, we can take our ER diagrams and convert them into a relational model and then into a relational database. But before we convert it into a relational database, often schema refinement is needed. We need to refine our designs further to make sure that the design is good. There is no redundancy of data. So our focus here is really on redundancy of data and ensuring that when we perform operations such as updating some information, insertions, deletions, it doesn't result in some kind of anomalies or inconsistencies in the data. So basically this refinement process is based on there is a specific theory in how it's done, and there is a systematic approach to it, and that's what we're going to take a look at in this video. Now we'll look at some designs that are not good and how they can be refined to make them a good design. So not all designs are equally good. We need to understand that. Also, when we come up with the ER diagrams, there's different possible designs. So when the relational schema is generated, we really need to analyze and make sure that it is a good design. So here in this example, we see information about students and courses. So say it's a relation called something, we've called it just stuff, and say we put all of the information into it about the student as well as about the course. So here we have the student ID, student name, serial number for the course, it's basically serial number for the course, the subject to which this course belongs, a course ID, and then the expected grade for the student in the course. Now so we have everything in one relation, both information about the student as well as information about the course. And if you think about it, this is a poor schema design, and the reason for that is this could lead to redundancy of data. So for every course that a student enrolls into, there's going to be repetition of the student's information, student's name, and if there was other kinds of information, they're getting repeated. The same thing goes for courses. Multiple students can register in a course, so information such as the subject and the CID of the course are getting repeated unnecessarily. So and that could lead to anomalies during insertions and updates. If say a student's name changes, then what that means is all of the records in the table where that student is referenced will have to be changed. So so then can we do better? What would an alternate design look like? So here's an alternate one wherein we have the student ID and name in a separate table called the student table. The course serial number and course ID is another separate table. The subject to which each of the courses belong is a separate table, and then enrollment information of a student in a particular serial number of the course. So the serial number is different from the course ID. Serial number changes for every offering of the course during multiple semesters. So the enrollment information is what in this third table, in the fourth table, where the expected grade, the specific grade of that student is also available for that particular offering of the course. So with the second design, as you can see, we are avoiding redundant data, and we are avoiding any kind of inconsistencies getting introduced into the data when insertions and deletions happen. So again, focusing on the bad design that we saw earlier. So this is an sample instance data. So what happens is for student Sam, you see there's multiple entries for the student Sam because he has enrolled in multiple courses, in an AI course and in an operating systems course. We see that there's some information over there getting repeated. Also we see that the information that the course ID 505 belongs to the subject operating system is repeated in multiple rows. So these are the kind of things that we want to avoid, and that's the reason we want to go through a schema refinement. Now, in order to do schema refinement, we're heavily going to rely on keys and what's called functional dependencies. So we'll look at functional dependencies in detail in this video. So basically, functional dependencies are key-like relationships, and what it defines is that so a key is basically a set of attributes, and what we know already is that if the key, if there are multiple tuples where the keys match, then we know that the entire tuples must match. So that's the we know that that's the key constraint. If the key value is the same, then the entire tuple must be the same. So functional dependency is similar to that. It's a further generalization, wherein what we say that if an attribute set, so by an attribute set, what I mean is it could be multiple attributes put together to form a set. So if an attribute set determines another, it's written as A determines B. So this is read as A determines B. So what this means is if there are two tuples that agree on the attribute set A, which means they have the exact same values for the attribute set A, then they must agree on B as well. So they must have the same values for the attribute set B as well. For the example that we looked at earlier, the student and course, we say that the SID, student ID, determines name. So what that means is if there are tuples where the SID matches, that is there's agreement on the SID attribute, then that means that there must be agreement on the name attribute as well. So the name also must be the same. So that's what's functional dependencies. Now, what other functional dependencies were there in that particular data set? So let's go back to see. So we had SID and name, so there's a functional dependency between them. There's also a functional dependency between CID and subject. So CID determines subject. So if there are tuples where the CID matches, then the subject also must match. So those are examples of our functional dependencies. And functional dependencies, they are independent of the schema design choice, or what kind of choices are made. We can look for these kind of relationships in any kind of schema that's available. So to formally define functional dependency, or FD, as the acronym for it, the way it's defined is given a relational schema R. So given a relational schema R, the and subsets X and Y of R. So basically X and Y are attribute sets. That's what we mean here. Attribute sets pulled out from the relation R. So the definition is that an instance of R satisfies the functional dependency X determines Y if for any two tuples T1 and T2 in R, if the values of X in both the tuples is the same, then that implies that the values for the Y attribute of those two tuples also must be the same. So to put this in perspective, say here's a relation R, and say here's our attribute A1, A2 and A3. So the attributes A1 and A2 say are X, and the attribute A3 represents the set Y. And if we have two tuples, say T1 and T2, what this means is if the values of X in T1 and T2 agree, so say we have the same kind of values, and I'm just using some numbers here, then the value that is in A3, the Y attribute set must also match in both of those tuples. So that's what it means, and this is the formal definition for FDs. So For an FD to hold for a given schema R, it must hold on every possible instance of R. So it's not specific to one particular instance, but it must hold. The functional dependency must hold for all instances of R. So here's a picture that demonstrates the same thing. So we have the relation R, two tuples T1 and T2. We have a set of attributes X and a set of attributes Y. We say that if the tuples T1 and T2 agree on the X values, then they must agree on the Y values as well. And that's when the functional dependency is said to hold, and it's said that X determines Y. Here's an example. This is a different one. We're using a movies database here, and what we have is the title of the movie, the year in which it was released, the length, film type, the studio name where it was produced, and then a star name, an actor from the movie. So given this, there are some functional dependencies that we can assert based on this given relation. So as we can see, if the title and year in two tuples are the same, then the length value is also the same. As you can see in the first two, in fact the first three rows, we see that the title and year, when the values agree, then the length also agrees. So basically from that we can assert that title and year, these two attributes together, determine the length of the movie. Now we can also see that title and year also determine the film type, so the film type also doesn't change. Title and year also determine the studio name. But then if you look at title and year, Star Wars 1977 doesn't necessarily determine the star name, because the same movie could have two actors, and so there's different star name over in the last column. So this last one is not a functional dependency for this particular relation, but these first three that we saw are valid functional dependencies. So here we'll use another example of hourly employees from the employee database. So the kind of information that we have about hourly employees is their SSN number, their name, there is a lot information, rating, that is rating of their work, hourly wages, which is determined by the rating, and the number of hours worked. So for ease of explanation, we're going to use the SNLRWH notation. What that means is those are the attributes, the listing of the attributes. It's really the set of attributes. S stands for SSN, N for name, L for lot, R for rating, W for wages, and then H for the number of hours worked. So now we will and then the entire we have the entire relation itself. So the relation name is hourly employees. So that's our relation, and then the SNLRWH is our attribute set, the set of attributes that we have. So we will use this and look at some of the constraints and functional dependencies on it. So as we know, S is the SSN, so and it is the key for the table. It is underlined over here, so it's the key. Because S is the key, what that means is S determines all of the other attributes. So that's our first functional dependency. Always the primary key determines all of the other attributes in the table. So and we are familiar with that constraint already. So no two tuples can having same values of the primary key can exist in the table. So that value has to be unique. Next we see that rating determines hourly wages. So basically R determines W. So we'll continue with that, and here's an instance for that same relation. So we have our S, N, L, R, W, and H values. There's some instance data here. So we'll look at some problems that are caused due to a functional dependency that exists between R and W. We see that R determines W. So if the rating of the employee is 8, then the hourly rate that this employee earns is 10. So we see that wherever the rating is 8, the wages are 10. If the rating goes down to 5, then the wages are 7. So we see that there is that functional dependency where R determines W. Now, so what are the issues with this functional dependency? So basically in schema refinement, what we're doing is we're looking for these functional dependencies and see if that causes any issues in the database. Does it cause inconsistencies? Does it cause anomalies? So in this case, there's an update anomaly. And the reason for that is, say we want to change the value of W, the wages per hour, in just the first tuple, then that's we can do that, but that's going to result in an anomaly. So say we want to change the wages for employees with a rating of 8 from 10 to 12, then now what that means is the update cannot just happen in one tuple, it has to happen in multiple tuples, otherwise it's going to result in an update anomaly. Insertion anomaly, say we want to insert a new employee. Say we want to insert a new employee into this table, and initially the rating of that employee is, say, 4. Now there's no way for us to know based on this information that we have. Now we don't know because there are no other rows with a rating of 4, so we don't know what the wage should be for employees with a rating of 4. So that's an insertion anomaly, and that's an issue with this kind of a design. Now with respect to deletion, say we want to delete all the employees that have a rating of 5, and if we go ahead and do that, and if we delete those two tuples there, then along with that we are losing the information about the wage for a rating of 5. And later on, if we want to insert new employees with a rating of 5, we've lost the information that the corresponding wage is 7. So those are the kind of issues that we want to avoid, and that's the reason we analyze functional dependencies as part of schema refinement, and then try to come up with a better schema design and avoid these anomalies. So the solution for that is basically to pull out the attributes that are causing the functional dependency and causing anomalies due to the functional dependency, which is in this case the rating and the wage. So that's independent of the rest of the employee information, so that can be pulled out into a separate table. And in that way, in the employee table, we just maintain the rating for each employee, and then based on the second table where the hourly wage information is there, the wages paid to this employee can be calculated. So here the design can be fixed or refined by breaking up this first table into two tables, wherein the R and W attributes, those two columns, are pulled out into a separate table. So that's how we fix this issue. Now, in dealing with functional dependencies, there are different axioms that are used. So basically, we use what are called Armstrong's axioms and compute based on some existing functional dependencies. We're able to compute new ones. So the first axiom is the reflexivity rule, wherein what it says is that if y is a subset of x, then x determines y. Now this is a trivial dependency. So an example of this would be name comma student ID determine name. So because here you see that, so name is the y and it is a subset of x, and so x determines y. So that's the trivial reflexivity rule that applies, and then the combination of all of these axioms together help infer new functional dependencies. The second one is the augmentation axiom, wherein if x determines y, then we can add an attribute to both sides. Xw determines yw. So that's the augmentation rule. So say we have a serial number of a course determining the subject, then and we can add expected grade to both sides. A serial number and expected grade together determine the subject and expected grade. So if two tuples agree on serial number and expected grade, then they also will have to agree on the values of subject and expected grade. So that's the augmentation axiom. The next one is transitivity axiom, wherein if x determines y and y determines z, then we can infer that x determines z. So an example of this would be serial number determines course ID and course ID determines subject. So we can infer that serial number determines subject. So those are the axioms, and these reflexivity, augmentation and transitivity rules further lead to say the union and pseudo-transitivity rules. So in union we say if x determines y and x determines z, then x determines yz. So that's the union rule. And for pseudo-transitivity, if x determines y and wy determines z, then xw determines z. So we are basically extending, based on those previous axioms, we are extending and leading to union and pseudo transitivity. And then we also have the decomposition axiom. If x determines y and z is a subset of y, then x automatically determines z, the subset. So that's the decomposition rule. So now, based on these different axioms, we can come up with a closure of a set of FDs. So given some known FDs, we can apply all possible axioms and come up with its closure, called represented as F plus, which is the set of all possible FDs. So the formal definition is that if F is a set of FDs, its closure F plus is basically a set of all FDs x determines y, where such that it is derivable from given F and using all of Armstrong's axioms. So that's what F plus would be. Now, which of the following are in the closure of student course functional dependencies? So student course table is what we saw earlier with the SSN, name, lot, rating, wages per hour, and the number of hours worked. So that's, well, sorry, it's the student ID, name of the student, course ID, serial number, it's that one. We're referring to that example. And what we want to see is which of the FDs shown here belong to the closure. So name determines name. That's a trivial one, and it's true. Always two tuples agree on that same attribute value. Now CID, course ID determines subject, that belongs to the closure as well, as we saw from that previous table. Serial number for the course offering determines the subject, so we saw that that holds as well. Now course ID and student ID together, if two tuples agree on these values, then they must agree on subject. So that we see that that's also true. This is basically we've just added a new attribute to one of the sides, and the other side it still holds because we have CID determining subject. And then the last one that we have is course ID determines student ID. Now, if the course ID is the same in two tuples, does it determine the student ID? That's not the case. So there could be the same course could be enrolled in by multiple students. So this last FD does not belong to the closure of the student course table that we saw earlier. Next, we look at equivalence of functional dependency sets, and and how do we conclude that they're equivalent. So basically two sets of FDs, F and G, are considered to be equivalent if their closures are equal. So basically the way to do it is compute the closure of each of them and check if they're equal, then they're considered equivalent FD sets. So here there's an example where we have two sets that are equivalent. We have xy determining z, x determines y, and that's equivalent to x determines z and x determines y. And once we compute the closure of these, we'll see that we end up with the same closure. And to compute the closure, basically we're applying all possible Armstrong's axioms to come up with the full closure set. It's possible that in this case what will happen is the closure contains a huge number of functional dependencies, and it can be exponential in the size of the schema. If the schema has a number of attributes, then very quickly this closure can have a huge number of functional dependencies. So what we are really interested in for our purpose of schema refinement and coming up with a better design is computing the smallest possible representative FD set. So we want a minimal possible FD set that kind of covers all possible functional dependencies, instead of having a closure which is basically all possible combinations of the functional dependencies. So this minimal representative set is what's called the minimal cover. So an FD set F is considered a minimal if it's in such a manner, if the FDs in it are follow all of these rules, or all of these rules are satisfied. So if every functional dependency F in F is of the form x determines A, where A, the right hand side, is a single attribute, then it's considered minimal. So if every FD in F is of this form, then that's minimal. So basically we are expressing each FD in its simplest possible form. There's a single attribute on the right hand side. For no FD x determines A in F, if you remove that, if you remove it from F, it should not still be equivalent to F. So if there is no such functional dependency in the set wherein its removal is still causing it to be equivalent to F, then that's considered a minimal cover. And then the third rule is that for no FD x determines A in F, and Z being a subset of X, Z being a subset of X, if we remove X determines A, union Z determines A, and if we still end up with the same equivalent F set, then that's considered a minimal cover. So what we are doing with the second and third rules essentially is that in the each and every FD, each and every functional dependency that's there in the F set is absolutely essential to the cover. So we're keeping only those that are absolutely essential. So removal of any FDs, if it still results in it being equivalent to the set, and when we say equivalent, if you remember, you compute the closures of the two sets that you're comparing, and if the closures are the same, then we consider them to be equivalent. So that's what equivalence means. So if the removal of certain rules is still going to keep the closure the same, then it means that it was not a minimal cover in the first place. So we want to just keep the absolute essential FDs, or keep the FDs in their simplest possible form, like you see in this first rule where x determines A and A is a single attribute, then that's called a minimal cover. And F is a minimum cover for G if F is minimal and it is equivalent to G. So that's the idea. So the closure will still be equivalent. So here in this, so here's an example where the first one is a minimal cover, x determines Z and x determines Y, and it's a minimal cover for this second one where xy determines Z and x determines Y. So basically we are getting rid of any of the unessential FDs in there to obtain the minimal cover. Now why are we using Armstrong's axioms and functional dependencies? And the reason we are discussing this is because this theory is consistent and complete. So we can be sure that by applying these theories, we can have a consistent set of functional dependencies, and at the same time we can be sure that the set that we have is complete. So basically, using this, we will be able to come up with a better design for our schemas. So Armstrong's axioms, they derive all the FDs and only those FDs that should hold. That's the reason we are using them. So so that's all I have in this video. In the subsequent video, we'll go over how how the minimal cover is used to basically take a given schema design and further refine it. Thank you.